Section 3-2, entitled Definition of Derivative at a Point. The objective of this section is, given the equation of a function, use the definition of derivative to calculate algebraically the value of the derivative at a point. If you recall what we did in the first chapter of the book, the first two sections of that first chapter, we were approximating the derivative. And now we're going to talk about how we can find the exact value. No longer approximating it, finding the exact value. Let's start off by talking about some terms that we've seen so far to describe a derivative. This goes back to terms you saw back in Chapter 1. If you recall, in the first two sections there of Chapter 1, actually Section 2, we use the term rate of change to describe a derivative. A derivative is a rate of change. It tells you the rate. Another way that we described a derivative was an instantaneous rate, actually from Section 1. We use the term instantaneous rate. In fact, we even saw these two terms combined here to call it an instantaneous rate of change is another way to describe it. One of the techniques that we used to find a derivative graphically or approximate it graphically was to sketch the tangent line and then find the slope of that tangent line. The slope of that tangent line represents the rate of change, the instantaneous rate, the derivative. It's another way that we can describe a derivative. Here's a new term here for us probably, is difference quotient. We'll talk more about this in the next section, but another way for us to describe a derivative is a difference quotient. And what does that mean exactly? Well, if you go back to what slope is a change in y divided by a change in x. So you're dividing those two quantities. When you divide them, you get a quotient. And when we say that it's a change in y, we're talking about subtracting those two values. It's a difference when you find, or the result of subtraction is called a difference. So it's a change in y over a change in x. So the numerator is a difference, the denominator of your slope is a difference, and you're dividing those two, so you have a quotient of differences, or in other words, a difference quotient. And lastly, the last way we could describe here a derivative is it's a quotient of y over x. And that comes directly from slope. Slope is a change in y divided by a change in x, so it's a quotient of y's over x's. Remember, that's a big distinguishing factor for us between a derivative, which is a quotient of y over x, and a definite integral, which is a product of x and y. All right, let's take a look at an example here of a function, and we'll use this example to help us see how we're going to calculate this derivative exactly. All right, so it's going to go back to the techniques that we saw in the first chapter to help us do that. And we're going to apply some techniques that we saw in chapter 2 as well to help us find this derivative. So let's just sketch some function here. We'll say this is f of x. Doesn't really matter what our function looks like there, but we'll call that f of x. And let's say that we want to calculate the slope here at c. I should say the derivative at c. Let's name this point here as c, f of c then. And if you recall, what we did in chapter 1 to approximate that derivative is we went forward some distance. We'll call this x out here. And we'll mark this point up here on our curve as the point x, f of x. And what we did is we calculated the slope between those 2 points, which actually was calculating the slope of that line right there. All right, and that line actually is what we call a secant line, as opposed to a tangent line. A secant line gives you 2 points on your curve like this, versus a tangent line just touches your curve at 1 point, which is what we're trying to do. And so we found then the slope between these 2 points. Remember, slope, of course, is rise over run. It's one way to think of it. That is the change in the y's over the change in the x's. So using the names that we've come up with for these 2 points, we could say the change in y would be f of x minus f of c all over the change in the x's, which would be x minus c. So how we would calculate the slope of that line, or how we did calculate the slope of that line back in chapter 1. And then what we did is we took that interval and we said, let's make that now in a smaller interval. And then did it again for an even smaller interval. In other words, what we did is we took this point right here and forced it to head along the curve in this direction. We said, let's make the interval smaller and smaller and smaller. In other words, we were forcing x here to approach or get closer and closer to c. And the question is, what was happening as we were getting closer and closer and closer to c? And when we force x to approach this value of c, this is what we found out in chapter 2 was called a limit. So it turns out that if I use this formula that I have here for slope, f of x minus f of c all over x minus c, and I combine it with this idea of a limit forcing x to go to c, the two of those are going to give me a way to find the slope of the tangent line. So here is your definition of a derivative at a point. That is, x equals c is the point that we're talking about. We say that f prime of c, notice the notation that we're going to use here for a derivative. We'll use this throughout the rest of the book from here forward. Whenever we talk about a derivative, the way that we define that derivative is f prime. If your function is f of x, then its derivative is f prime. That notation comes to us through geometry. You may recall in geometry where you defined a point, for example, and then took a line and reflected that point across the line. If your point was named A, then the reflection of that point across that line was called A prime. And it was called that way so that you understood there was a relationship between the original point A and this transform point that was reflected across that line. The same is true here. We're using f prime because there's a relationship between our original function and its derivative. The derivative is telling us the slope of that function. So that'll be our notation. We read that off as f prime of c. So read as f prime of c. It's equal to what we just saw on the previous graph that we were sketching. It's the limit as x goes to c. That's what's making this interval smaller and smaller and smaller. Of f of x minus f of c all over x minus c. That's your slope formula. So we're taking the limit of this slope and forcing the 2 points to get closer and closer and closer to each other. And by doing so, we'll find the limit, this limit will find for us the slope or the derivative of this function. Okay. Let's take a look at an example and use that definition here to help us out. We're going to actually change the problem here slightly from what they said to do, but example 1 there on page 74 says the following. It says if f of x is equal to x squared minus 3x minus 4, find f prime at 5, the value of the derivative of if x equals 5, and check by graphing the difference quotient and finding the limit. Well, we're going to find the derivative of this thing by first using our definition. I'm going to say the next thing we want to do here is find the equation of the tangent line. We'll look at how we can do that. And we're going to graph those together. So I'm going to change the problem there slightly. All right, so let's start with A, which is finding the derivative, f prime of 5. So to find f prime of 5, I'm just going to go back to the definition that we just wrote down and write that down here. Of course, I'm replacing the c in that definition with 5. So I have the limit as x goes to 5 instead of x going to c. Of f of x minus f of 5 instead of f of c there, all over x minus 5 instead of x minus c. So I've just rewritten that definition, replacing replacing c with 5. All right, the next step of this is going to be some substitution. If the limit as x goes to 5, notice that I'm writing down my limit notation throughout the problem here until I get to the last step and I'm ready to substitute. As I let x go to 5, I'm going to replace f of x here with its function that we defined at the beginning. So that was x squared minus 3x minus 4. And f of 5, if I plug in 5 into this original function, I can find out what f of 5 is equal to. That would be 5 squared is 25, minus 3 times 5, that's minus 15. 25 minus 15 is 10. Minus 4 more, that is 6. So I've got a minus 6 that I put at the end there. So yeah, here's our f of x, here's our f of 5, and we're going to divide that by x minus 5. If you take the limit now as x goes to 5, I'm going to just rewrite this as x squared minus 3x minus 10. That's all divided by x minus 5. Now if you plug in 5, to see what value this is approaching, you'll get 5 squared minus 15 minus 10. That's going to 0 in the numerator. Over x minus 5, that's going to 0 in the denominator. In fact, if you go back to what we started with, in this form right here, f of x minus f of 5 all over x minus 5, plugging in 5, you'd have f of 5 minus f of 5, that's 0. Over 5 minus 5, that's 0. In other words, you start out with this thing in an indeterminate form, and it's going to take some work then for us to find out what value this limit has. All right? Now the fact that when I got to this point here and it's still in the indeterminate form, that tells me that when I plugged in 5 and I got a 0 out of the numerator, that x minus 5 must be a factor of it. So I can use that to my advantage. Knowing that x equals 5 is a 0, this tells me that x minus 5 must be a factor of it. So the other factor then would be x plus 2. And now if you look at what we have here, I've got x minus 5 over x minus 5. I'm going to cancel those two out. In fact, that's the whole reason that we were getting this indeterminate form. The reason this indeterminate form was showing up when I plug in 5 was because I must have had a factor of x minus 5 in the numerator and a factor of x minus 5 in the denominator, so that when I plug those the 5 in, I was getting 0 over 0. Once I eliminate those, I've now gotten rid of the indeterminate form. I can actually evaluate this limit. Notice I won't write my limit notation. The limit is x goes to 5 down because I'm going to actually substitute that in. I'll end up with 5 plus 2. I'll go ahead and write it this way just so you see that we're actually substituting in the 5 for x there. 5 plus 2, of course, is equal to 7. This is different than what we did in the first chapter. In the first chapter, we were coming up with values that were getting closer and closer to the derivative for us. In fact, we were getting values that would be closer and closer to this value of 7. We're not saying the derivative here is approximately 7 or it's close to 7 or my best guess is 7. We're saying the derivative is equal to 7 here. It's the exact value. Takes a little more work to get that, but the advantage at the end is I get the exact solution. All right, so that's the first step. The next step that we said we wanted to do in this problem was, part B, find the equation of the tangent line. Now again, just to graph what we've come up with here, you've got a function, x squared minus 3x minus 4. And x squared minus 3x minus 4. In fact, let's go ahead and just factor that just so we can get a little more accurate sketch of this thing. So this has factors of 4 and 1 here. So it's x minus 4 and x plus 1 are the two factors. I should say the two zeros are at 4 and negative 1. So that gives me a little bit of a hint as to what this thing looks like. So it crosses here at negative 1 and at 4. So it does something like this. It's a parabola, of course, that opens upward, and it has that shape there. So what we found as a result of part of the first part here, part A of this problem, I marked out here at 5, that at x equals 5, I found that the slope at that point, in particular the slope of the tangent line at that point, is equal to 7. Slope of that tangent line is 7. So the question is, can I come up with the equation of that tangent line? I know a point that it goes through. It goes through this point here, which is both on my tangent line as well as my original function. And I know the slope of that line. That should be enough information for me to find the equation. So let's see if we can do that. It's a straight line, so I know the equation is in the form of y equals mx plus b. I just need two things here. I need to know a point that it goes through, which I can find. I know it goes through the same point on my tangent line as it does at the function at x equals 5. So if I find out what f of 5 is equal to, which technically we actually did already, if I scroll back up here, notice that in this original limit, we took f of x minus f of 5, so I've already actually done the work there and got that is 6. You could plug it in again and obviously get 6 out of it would be fine too, but I've already done the work for it, so let's just write that down. So in other words, I'm saying that when x is 5, y is 6 there, so I have a point. The other piece that we need in order to come up with the equation of this line is the slope. And I've already done that. F prime of 5 is the slope, and we found out that was equal to 7. Those are the two pieces of information that I need in order to come up with the equation of this line. I'm going to take these two pieces and put them together, and we're going to use the point slope formula to do that. Now, you might have another way that you prefer doing this, and that's fine. I'm going to use point slope formula because as it's named there, if you know the point and you know the slope, it tells you the equation of the line. It's y minus y1 is equal to m times x minus x1. So y minus y1 is the 6, is equal to m, your slope is 7, times x minus x1, which is the 5. And technically, you can leave your answer just like that. Usually we want to solve it for y, but you could leave it in that original form. I'll go ahead and solve it for y. You've got 7x. You'll have a minus 35 on the right side, and I'm going to add 6 to it. So it'll be a minus 29. 7x 29 minus 29 is the equation of that tangent line that we sketched up here. Okay? And now part C then of this was to actually graph this on your calculator. So let's try that out. So in y equals, let's put in the original function, which was x squared minus 3x minus 4.